a landscape like this, crops thriving in the sun, winds sweeping across the hills, and just over the horizon, cities running on electricity. Sustaining all of this requires a massive, continuous flow of energy. But whether it's the sunlight feeding these plants or the power grid lighting up a classroom, those distinct sources of energy trace back to the same microscopic origin, the nucleus of an atom. Atoms act as the universe's invisible engines. To reach a state of stability, they constantly shift, break apart, and transform their physical identities to move closer to a more balanced state. This graph maps the binding energy curve, illustrating a core physical rule. Nature seeks maximum stability, peaking right here at iron. Unstable heavy atoms on the right break down to move toward iron. Light atoms on the left join together to move up the curve. This relentless physical pursuit of iron stability is what drives the three main nuclear processes: splitting apart, joining together, and spontaneously decaying. Let's start with joining together. Nuclear fusion occurs when small, light atoms are forced to merge, forming a single, heavier, and more stable nucleus, like hydrogen turning into helium. There is a severe physical obstacle here. Because atomic nuclei are positively charged, they violently repel each other. To make them fuse, we have to force them past this magnetic barrier. Overcoming that repulsion requires millions of degrees of heat and immense pressure. These are conditions found naturally inside the cores of stars, like our Sun. We cannot yet maintain nuclear fusion in a power plant on Earth for a very practical reason. We lack a physical vessel that can hold fuel burning at millions of degrees without the containment walls melting. Scientists are racing to solve this because fusion yields immense heat and produces safe helium with zero radioactive waste. For now, that clean energy travels across space to drive our equatorial ecosystems from a distance. If fusion is joining light atoms, nuclear fission is the opposite. This is where massive, heavy, and unstable atoms split apart to become smaller. Fission happens when a heavy nucleus, like uranium-235, absorbs a wandering neutron, causing it to wobble violently and break in half, and release a massive amount of heat and kinetic energy. Crucially, that split also ejects extra neutrons. If you have a critical mass, the minimum amount of fuel required, those newly ejected neutrons will hit neighboring atoms, causing them to split as well. This creates an exponential geometric chain reaction. To prevent that chain reaction from accelerating into an explosion, nuclear reactors use control rods. By inserting rods made of materials like boron or cadmium, operators soak up those excess neutrons and strictly limit the reaction rate. Throttling that chain reaction keeps the nuclear fire at a steady state. We harness that controlled heat to boil water, spin turbines, and provide reliable electricity for developing power grids. Both fission and fusion require a physical trigger, a neutron impact, or extreme heat. Radioactive decay, however, is a spontaneous choice made by an unstable atom to shed energy and become more stable. In alpha decay, an unstable nucleus ejects 2 protons and 2 neutrons, changing its identity on the periodic table. In beta decay, a neutron converts into a proton by ejecting a high-speed electron. Because it gains a proton, carbon-14 turns into nitrogen-14. After these ejections, the nucleus is often still vibrating with excess energy. It settles down by releasing a gamma ray, a burst of pure energy, allowing it to reach a stable state without changing the element again. This spontaneous decay allows us to read the physical world. Living things, like the trees and grasses in these plains, constantly absorb carbon-14 from the atmosphere. The moment an organism dies, that intake stops. The carbon-14 trapped inside the remains then begins to undergo beta decay. Because this happens at a steady, mathematically predictable rate, scientists can measure how much is left to calculate how long ago the organism lived. Spontaneous radioactive decay provides an invisible clock buried in the soil and the biosphere, allowing us to accurately date the remains of ancient organisms and reconstruct the timelines of our natural history. This table lets us compare these 3 nuclear processes side by side. Fission requires a neutron impact to split heavy atoms. Fusion requires extreme heat to join light atoms. And decay is the spontaneous stabilization of an individual nucleus over time. Their real-world impacts are everywhere. Fusion powers the stars. Fission provides massive, controlled energy for our electrical grids. And decay acts as a historical clock in the fossils and artifacts left behind. From the sunlight hitting a banana plantation to the power running a city hospital, nature's microscopic quest for atomic stability shapes our environment, preserves our history, and dictates how we harness energy in the years ahead. To explore more about the physics driving our world, find more educational content at the Yaka Digital Network platform by visiting www.yaka.cc.